Okay, we're starting the chapter on acids and bases, and we'll for sure have a test on this, and may start another chapter, and that would be on the final. I don't know if we'll get 2 tests in, because we combine 15, and then there's really just one section out of 16 that you have to do. And that just reminds me. Oh, I think maybe I forgot to change the chapter until. If you are going or contemplating doing the musical chairs Friday, it's during 4th and 5th period, so you'll take your quiz before you do musical chairs. Or if you have a study hall that afternoon, but it needs to be done Friday. Okay. Acids and bases. So we're going to talk about some of the properties of acids and bases, review over the nomenclature, which we did way back at the beginning of the year. I think it was chapter 2. Okay, so we'll review over that, and also talk about the conjugate acid-base pairs. So acids have a sour taste. What's an acid that you taste? Lemons have citric acid and stuff, yep. So it has a sour taste. They react with certain metals to release the hydrogen. So acid will usually have a hydrogen as its cation, and when it reacts with the metal, it releases that hydrogen and creates some sort of metal salt. It reacts with carbonates and bicarbonates to produce carbon dioxide. And then it will turn litmus red. If you have litmus paper, it'll turn litmus paper red. We'll use little strips of pH paper, but ours will actually have different color, a graduated color change, and you can actually determine pH from those. Bases have a bitter taste, like soap. Did any of your parents make you eat soap when you were little? Yeah. They feel slippery, like soap has the slippery. What else? Sometimes get on. Can't think of. Okay. And then it would turn litmus blue instead of red. And we're going to talk about 3 different definitions. There's the Arrhenius theory or definition, Arrhenius theory, the Bronsted-Lowry definition, which that's probably one we'll spend the most time on, and then a Lewis definition of the acids and bases. So the Arrhenius acid definition is that acids would produce hydrogen in water, and when it's in water, the hydrogen that it produces will automatically attach to the water and would produce hydronium, H3O+. So when we talk about H3O+ and H+, they're really interchangeable. Because whenever you produce a proton, it automatically attaches to water that's in that solution and forms hydronium. An Arrhenius base would produce hydroxide in water. So this base would take the hydrogen off of the water and produce the OH group and then a cation. In this case, it's a cation. So it produces hydroxide in water. Now, when we were doing nomenclature, remember we said that bases have an OH group in it? This is our base, NH3. It does not have an OH group in it. So for an Arrhenius base, you do not have to have an OH group present. And it just has to produce hydroxide, so it's taking the hydrogen off of water and producing hydroxide. So remember back to nomenclature. Ooh, that yellow is really hard to read. Acids with hydrogen and a nonmetal are named with the prefix hydro and end with an IDE ending, an ID or IC ic, an ic ending. So HCl, it's hydrogen plus a nonmetal. Hydrogen and chlorine would be hydrochloric acid. Let me see if I can change the color of that font fast. little easier to see up here. Okay, so hydrochloric acid. Remember, if you have a binary acid, just the two elements, then it's hydro and then an IC ending. This jog your memory back to the beginning of the year. Acids with hydrogen and a polyatomic ion are named by changing the end of the name of the polyatomic ion from ate to ic or ite to us. So remember, you look up the polyatomic ion ClO3, the name is chlorate. So if we add a hydrogen to it, it would be chloric acid. We change the ATE to an IC ending. ClO2, though, is a chlorite ion, and you add a hydrogen to it, and it would be chlorous acid. And when you look up the polyatomic ion, if there's already a prefix like perchlorate, you just leave that prefix alone. You keep it, so it would be perchloric acid. So ATE to ic, ITE to us. This table just shows a lot of the different acids from their anion here. Bases with the hydroxide ion are named as the hydroxide of the metal in the formula. So NaOH is just sodium hydroxide, potassium hydroxide. It's a normal nomenclature. Why is there two here? Two hydroxides. Why? Because barium has what charge? Has a 2+ charge. A hydroxide is a -1, so barium must be a 2+. So this, in this case, iron is a 3+. Why is there a 3 Roman numeral? Right. Two different kinds of irons, and you have to indicate which one it is. There's iron 2 and iron 3. And how do we know it's iron 3? 3 hydroxides makes 3-, which means in order to balance the charges, iron must have been 3+. So let's name these acids. What's the first one? Would we use hydro? No, because it's a polyatomic ion. So you have to look up NO2. It's not, NO2 is nitrite, so it's nitrous acid. How about the second one? This one? Because SO4 is sulfate, becomes sulfuric acid. HiO3. IO3 is iodate, so it would be iodic acid. And last one? Okay. So hopefully you remember how to do that. The Bronsted-Lowry definition. Bronsted acids donate a proton. So really it's the same. We can use the same example as the Arrhenius acid and base because it's donating a proton, but Bronsted bases, it's all about accepting a proton, not creating the OH. In this case, it's creating an OH. It won't always create hydroxide in solution, but this is the base because it's going to be the acceptor. So acids donate, bases accept. AD and BA. Acids donate, bases accept. And that's for the Bronsted-Lowry definition. Oh, it's putting up the labels. The base, the acid, because the acid is donating a proton to the NH3. In any reaction, acid-base reaction, there's two conjugate acid-base pairs. So they're paired up with the form that it is before. Remington, put your iPad away. What it was before and then what it is after you have either gained or lost that proton. So each pair is related by the gain or loss of hydrogen. One pair occurs in the forward reaction, one pair in the reverse. So this is a conjugate acid-base pair. The A is just standing for the anion, and hydrogen is your cation. So HA is your acid because it's going to donate the proton, and it becomes the A-. So this is our first conjugate acid-base pair. Here's our acid, and this is the conjugate base. This is our base. It's accepting the proton and becoming the BH+. So this is our base, and this is called our conjugate acid. So this is, let's write this. This is acid, and this is our base. But the acid is paired with the conjugate base. And this is the conjugate acid. The reason why it's called a conjugate base instead of the conjugate acid is that in order to go backwards from this A- back to the HA, it has to act like a base in order to get back to its original form. And so that's why it's called a conjugate base. Same thing, BH+ has to donate a proton in order to get back to its original form. So it's considered a conjugate acid because it has to donate the proton. Does that make sense? Anyone have questions on how to pair them? These come in are very important in buffer systems, which we may or may not get to. But we will, the buffer system, does anyone know what a buffer is? Do you guys talk about buffers in biology? Maybe? They resist. It's a solution that resists a change in pH, because if it would have an acid in solution and the conjugate acid in solution, so if I added a base to the solution, then this conjugate acid would donate its proton and make it neutral. If I added an acid and vice versa, they're able to donate and accept protons from whatever you add to that solution, in order to keep that solution's pH from changing. So that's why conjugate acid bases are pretty important. So in this acid-base reaction, HF donates a proton and it forms the conjugate base F-. Water here accepts hydrogen to form H3O+. So this is if it accepts a proton, it acts as a base. So this is a base and the conjugate acid. Sometimes, oh, never mind, that's not on this. I thought it was. So here, it just shows the acid and base, acid conjugate base pair. Let's see. Can I switch it? This is just another figure showing how you add and subtract protons to get from the acid to conjugate base or base to conjugate acid. Same thing. Okay. So here, NH3 becomes NH4. So it has accepted a proton and it acts as an acid or base. Right, this is the base because it accepts the proton, correct? And so this would be the conjugate acid. Water is acting as the acid in this case, and it becomes the conjugate base over here, the OH. In the previous one, so water is the acid here. Water was the base here. So water can act as both an acid and a base. You have to check in the solution, in the reaction, which it is acting as. Okay, so we're supposed to write the conjugate base of these acids. So if we're going to write a conjugate base, that means that these have to be acids, correct?
Yeah.
Okay. So what would be our Br minus? Don't forget to put your charge. What would this one be? Right. We're just losing one proton. We'll talk later. These are called diprotic acids, and they lose their protons in 2 different steps. So we're just going to do one proton. HCO3 minus. What would be the conjugate acid? Meaning these must be acting like a base, so they have to accept a proton. NO2. We have to add a proton, correct? What would this one be? NH4. This one has a plus because it's neutral to start with, and okay, so number 1, is this an acid conjugate base, or an acid-base conjugate pair?
Yes.
Yes, this one is a yes. How about this one?
No.
This one? No, the polyatomic ions are different here. This one?
Yes.
And this one? Yes. Okay. And that was all the notes that we're going to take. Questions at all?